Welcome, ladies and gentlemen, to this video lecture. Okay, so let us return to the definition of a limit and let us discuss the intuition behind the definition of a limit. So once again, let a and l be real numbers, let f be a function defined on an open interval containing a, except possibly at a. And by the limit as x tends to f of x equal to L, we mean the following. And this is something you need to have memorized. For every epsilon greater than 0, there exists a delta greater than 0, so that if x is within a delta distance of a, then the function values f of x is within an epsilon distance of L. So here we have the definition of this limit. Okay, let us discuss intuitively what this means at the hand of an example. So let's take a look at the following function. So let's define function from R without 2. So all the real numbers except for 2. So this symbol means everything in R except for 2, which maps to R. And we define f of x as x squared. And this is for all x in R without 2. Okay, so let us talk about this following limit. The limit as x tends to 2 of f of x, intuitively that is 4. So notice here this function is not defined at 2 because 2 is not in its domain. But the limit as x tends to 2 of f of x is 4. So let's draw the graph of this function. 1 is over there, 2 is over there. The domain does not include 2, so there's a little hole in there. And this is the graph of this function is of course a parabola. So here at 4, there will be a hole in the graph there, and the graph of this function kind of looks something like that. So a little parabola. Okay, and now previously limits will have been explained to you as saying that as we get closer and closer to 2, the function values get closer and closer to 4 over there. And the definition of a limit is a way of making this intuitive statement, which is up to interpretation, making that perfectly rigorous and taking any opinion out of it. Okay, so let us talk about what this statement means. For every epsilon there exists a delta, so that if x minus a in absolute value is less than delta but greater than 0, then f of x minus L is less than epsilon. So let's get an intuitive grasp on what that means. So instead of working on this diagram, what I'm going to do is I'm going to take the y-axis here and detach it from this system from these axes and place it also horizontally. So I'm going to take out this y-axis and I'm going to just move it horizontally like so. So here we have 2 number lines. 1, 2, 3, 4, 5, etc. Minus 1 is over there. 1, 2, 3, 4, 5, etc. 1, 2, 3, 4, 5, etc. And of course, the 2 is not included in the domain of this function. And now, what we should think of is that this function f defines a rule of going from elements in its domain to elements in what is called its codomain. So, for those of you interested, this set is called the codomain of f. And it's very simple. You just do the obvious thing. So, if you take a look at where this function f sends 0, 0 squared is of course 0. So 0 goes to 0, 1 goes to 1, 2 is not defined, 3 goes to 9, which is over there somewhere, etc., etc. So every point here in the domain is sent to some point here in the codomain. And if 2 were in the domain, 2 is not in the domain of the function, it would be sent to 4. And points close to 2 will be sent to points close to f, close to 4. So this point is sent to a point there. Okay, so now we want to make rigorous what it means to say as x approaches 2, f of x approaches 4. Let us think about this. Let us think about where all the numbers, let's take all these numbers, the numbers from 1 to 3 but excluding 2. Let us think about where all these numbers go. So let's think about all these numbers. So in the open interval from 1 to 3 but excluding 2. So 1 of course goes to 1, 3 goes to 9 down there somewhere, 2 doesn't go anywhere because it's not in the domain, but numbers close to 2 go to 4 over here. So we can ask ourselves, where do these numbers go? Each one of these numbers. So they go like so. And if you're close to 3, then they go to 9 over there. So this interval, excluding its center, so here the interval of, we say, of radius 1 centered at 2, everything in here is mapped to some interval in the codomain, in this case from 1 to 9. So the whole thing is mapped there. Okay. So you can think of we are restricting our view around an interval about 2 and looking where these numbers go. And now we can discuss the intuitive meaning of the definition of the limit. So we, of course, we can intuitively say that f of x, the limit as f of x, is equal to 4. That is what our intuition tells us. So let us interpret the definition of what this statement actually means in this number line context. So let's rewrite that again. For every epsilon greater than 0, there exists a delta greater than 0, so that if 0 is less than x minus a less than delta, then f of x minus L, or in this case 4. So A is 2 and L is 4, is less than epsilon. So this is what that means. So let's redraw this number line, and 0 over there, 2 over there, 3, 4, 5, 6, 7, 3, 4, 5, and let's draw the codomain. I missed 1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So let us think about what this definition says. It says that the limit as x tends to 2 of f of x is equal to 4. So here we have 2, and it says essentially, intuitively, what it says, numbers close to 2 will be close to 4. Will be sent to numbers that are close to 4. Okay, and what you should think of, these expressions, these absolute values. The absolute value measures the distance of a number x to the number 2. And here, the absolute value of f of x minus 4, that measures the distance of f of x to 4. So let us translate this statement with this intuition. It says, for every epsilon there exists a delta, so that if the distance of x to 2 is bigger than 0 but less than delta, then the distance of the function value to 4 is less than epsilon. So what it says here is, for any epsilon, if we look at this interval over here with radius epsilon, so let's write that down. This will be 4 minus epsilon, 4 plus epsilon. If we look at this open interval, let me color it like so. For any epsilon, there exists a delta. Let's use a different color. Let's use blue. There exists a delta, so that if we look at the interval of radius delta around 2, but not including 2. So if this is radius delta, let's write down explicitly what this is. If we look at the open interval of 2 minus delta to 2 plus delta, if we look at this interval but excluding 2 itself, that is what we have over here. This if the distance of x to 2 is strictly positive, x cannot be equal to 2, because then the distance of x to 2 would be equal to 0. So we're looking at all the numbers in this interval excluding 2. If we look at this interval, then all the numbers here are mapped into this interval of radius epsilon there. Okay, and we should be able to do this for every epsilon. We should be able to find a delta which does this. So it does not matter how big or how small this epsilon is, we should be able to find a delta which does this job, so that everything in this interval around 2 maps into this interval around 4. So for example, let's do that again. We've got 0, 1, 2, 3, 4, etc. 0, 1, 2, 3, 4, 5, 6, etc. So let's see. If we take epsilon example, if So for epsilon equal to 1, let's take a look at this interval from 3 to 5, or if you will, 4 minus 1, 5 plus 1. So for this epsilon equal to 1, we should be able to find an interval around 2, but not including 2, which maps into this interval. And let's see, what will that be? If we let's think about this a little bit. What goes to 3 here? 3. The square root of 3 goes to 3 over there, and the square root of 5 goes over there. So if we take any interval that is smaller or fits in between these two numbers, square root 3 and square root 5, any one of those intervals, then if we look at these numbers excluding 2, they will be mapping into this interval over here, like so. And we should be able to do that for any epsilon. So you should think of this as a game. You claim that that the limit as x tends to 2, the limit as x tends to 2 of f of x is equal to 4. Someone does not believe you. They say, oh, I don't believe you. How close do you need to be to 2 so that the function value is close to 4? So 2 is over there, 0, 1, 2, 3, 4 is over there. So someone says, I don't believe you. I don't believe that you can show that the function values is within a 10 millionth of 4. How close do you need to be to 2 to be within a 10 millionth of 4? So if you look at a very tiny interval around 4 minus 10 million, a million is 10 to the 6th, 10 millionth is 10 to the minus 7. So if we have look at a very tiny interval around 4, 10 to the minus 7. How close should we be to 2 to ensure that we map into this very small interval? I am now exaggerating its size here. How close should we be to 2 so that everything in this interval, excluding 2, maps into that interval? So that is the game that we are playing. We should be able to find an interval here, so that doesn't matter what number we take inside of this interval, all of these numbers are contained in this interval. And this is how we make explicit our let's say our intuitive explanation of what a limit is. Our intuitive explanation says if we get very close to 2, then we are very close to 4. If we look at our definition here, this is exactly what that definition says. If we are very close to 2 within a delta distance of 2, then we are very close to 4 within an epsilon distance of 4. So this implication captures that intuition. The tricky part here is these quantifiers. For every epsilon there exists a delta. So if you take any epsilon, doesn't matter, for example this one, you should be able to find a delta here, so that if you look at the interval of radius delta around 2, everything in this interval should be mapped into that interval. There's no element here that maps outside of that interval. That should never happen. If that happens, then the limit does not exist. So everything in this interval should map into the given interval. And this should hold for every epsilon. So let's erase all of those. If we choose a different epsilon, that should still hold. For example, if we choose this epsilon, we should be able to find a delta, so that if we look at the delta interval, or the interval of radius delta around 2, all of these elements should map into that interval. And it should not matter, it may not matter what the radius of this interval that we choose here should be. For any positive radius, we should be able to find an interval here that everything in here maps there. So we should be able to find an interval for 10 to the minus 100. So if epsilon is 10 to the minus 100, we should be able to construct a delta, very small delta, around 2 here, which maps into the interval over there. Everything in this interval should map into the interval of radius epsilon there. Okay, so that is the intuitive idea behind a limit. Let's do that one more time. So for every epsilon, so 0, 1, 2, 3, 4, 1, 2, 3, 4, 4 is over there. For every epsilon, if we look at the interval of radius epsilon around our limiting value, in this case 4, we should be able to find a delta, so that if we look at the interval around 2, oops, if we look at the interval around 2, except at 2, then every value here maps into that interval. So given an epsilon, find a delta, so that if you look at all points within a delta distance of 2, then the distance of the function value at that point and 4, if you look at the distance of the function value to 4, that has to be less than epsilon. Okay. And this is a little bit difficult to wrap your head around, and let me reiterate here, this is not because you are stupid, this is because this stuff is really hard. Let us think a little bit about how far limiting processes have come. So one of the first people to consider limiting processes like this was Archimedes. So very famously, Archimedes computed the volume of a sphere compared to the volume of a cylinder, and that is actually that was actually inscribed on his gravestone. Let's see when Archimedes actually lived. He was born about 300 years before Christ in Syracuse in Sicily, which is part of Italy these days. So Archimedes was one of the first people to ever touch on limits. And formal limits, they were first defined by people around the time when Augustin Cauchy lived. So he was a French mathematician, and he was one of the first people to start working with rigorous with a rigorous definition of limits. But still, he actually made very, very crucial mistakes in working with limits and in developing the theory of analysis. And let's just take a look here. When did he live? He lived about from 1789, died in 1857, which makes it about 2,000 years. So the development of the work that we are studying now was developed over 2,000 years. It took people 2,000 years to come to grips with limits. We expect you to come to grips with limits in a semester. The softie in me thinks that is not entirely realistic. And from my own experience, it was a frustrating journey to come to grips with 2,000 years worth of knowledge. So let me warn you, it will be a frustrating journey. That is not because you are stupid. That is because this stuff is so hard that it took humanity 2,000 years to get it right. So if you are frustrated by this, don't worry. That is not because you are stupid. That is because this stuff is hard. Okay, so that is a short, rambly introduction on the intuitive idea behind the definition of a limit. Okay, and now in the coming videos we shall start using the definition in rigorous proofs. I will see you in those videos.